Well, when I went on Google Images and searched for curl, I of course got many images that were entirely unrelated to the topic that we'll talk about here. Most of them were related to women's hairstyles. But when I went under Google Images and Google searched for curl and vorticity, then I got a lot of images that were relevant. And this one in particular is one that I selected. So curl is the operation of our del vector operator um, crossed with a vector field v, and it tells you the direction and the magnitude of twice the angular velocity at any given point in this velocity field. So in this diagram we have this vector field. I said velocity field, but I meant vector field. So this diagram depicts a 3D vector field, and whatever this vector is, it could be flow of air or water or something else entirely, but whatever it is, it's moving outward and to the right of the picture relatively fast near the top part of this box. And then there's a gradient in that flow rate where the flow reverses direction as you move towards the bottom of the box. And so at every single point in this box, if you were to put a particle, if this were a flowing air or water, if you put a particle in that flowing air or water, that particle would be both moving, translating with the flow, whether it's forward or backward. But in addition, the particle would be rotating. And it's rotating at a rate equal to its angular velocity. And the direction of the vorticity or curl is aligned with your thumb if you point your right hand with your fingers curled around the direction of the rotation. Okay, so the curl is directed in your thumb with your right hand fingers oriented in the direction of rotation. That's the direction of the curl. And the magnitude of the curl is equal to twice the angular momentum at each point in a vector field. So as after viewing this video, your aim will be able to compute the curl at any location in a vector field, and you'll also be able to explain the relationship between the pattern of the vector field and the curl at selected points. And this is chapter 16.5 of Greenberg. The topic is curl. And so the curl of a vector field is sometimes written as the word curl next to the vector, or it's also written, as I mentioned before, as the vector product of our vector operator del and the vector. And so using the same definition or way of remembering how to take a cross product, again, we make a matrix with the Cartesian unit vectors, the Cartesian base vectors, I should say, on the first row, I hat, j hat, and k hat. Then the components of del, remember, del was equal to d by dx in the I hat plus d by dy in the j hat plus d by dz in the k hat. We write the components of the first term in the second row, and then the components of the last term, which is a vector with 3 components, in the bottom row. And when we carry this out, we get I hat times the partial Vz with respect to y minus the partial of Vy with respect to z minus j hat times the partial of Vz with respect to x minus the partial of Vx with respect to z plus k hat times the partial of Vy with respect to x minus the partial of Vx with respect to y. And I did that rather quickly, but I hope you are able to work through this determinant operation and convince yourself that what I've written down is indeed correct. So these are some equations I'd like you to remember. It's probably easier to remember this particular relationship than this. So here's an example of how to compute the curl of a vector field. So say we're given the vector field. Again, V is equal to Vx in the I hat direction in general, Vy in the j hat direction, plus Vz in the k hat direction. And each of these components can vary with x, y, and z in x, y, and z space. And in this example, we're going to say that Vx is equal to x, y, and z. Okay, so this is Vx. Vy is 0. And then Vz is minus 2y squared t, where t is time. Right? And so this is Vz. So going back to evaluating the curl of this, again, I don't like to memorize equations, but I do. It's easier for me to remember how to set up this matrix and take the determinant. And again, Vx is x, y, z. Vy is 0, and Vz is minus 2y squared t. And when we take the determinant of that, we get I hat times the derivative with respect of y of minus 2y squared t, and that gives minus 4yt. And then the derivative of 0 with respect to 0 is 0. The derivative of 0 with respect to z is 0. And then we have minus j hat times the derivative of minus 2yt with respect to x, which is 0, minus the derivative of xyz with respect to z, and that gives minus x and y. And then we have k hat times the derivative of 0 with respect to x, and that's 0, minus the derivative xyz with respect to y, and that gives minus x and z. And so the answer is minus 4y t I hat plus xy j hat plus, or I should say minus, xz k hat. And again, as I mentioned before, the curl is always a vector property. And I'll explain in a minute why it tells you the magnitude and direction of angular velocity. And in this particular case, every component of the curl varies in space, and the x component, the I hat component of the vorticity, varies also in time. Again, t was time. So what is the meaning of the curl? what does the curl of V mean? So here's how I explain where it's related to angular velocity. So in this case, let's consider 2D plane flow. That is, we'll say Vz is equal to 0, and Vx and Vy only vary with x and y. They don't vary with z. So in other words, the velocity field is fully described by Vx as it varies in x and y, of course in the I hat direction, plus Vy as it varies in x and y, but not z in the j hat direction. And in that case, the curl of V is equal to dvy dx minus dvx dy in the k hat direction. So if you were to work this out, you would see that all the other terms are 0 except for these two terms and in the k hat direction. So what this tells you is that the curl is orthogonal to all the motion for 2D plane flow, or it's perpendicular to the plane. Well, I shouldn't say plane, it's perpendicular to the 2D flow. In other words, the flow is uniform as you vary z, it's uniform, but it's only in the x and y component, and it only varies in x and y. So the first aspect that we see of the curl formally is that it's perpendicular to the flow, to this 2D flow. So now let's consider a small box in our 2D plane flow. And one corner of our box is located at point X and point Y, and let's call that corner point O. And then point A is on the lower right-hand side of the box, and it's located at X plus delta X. So our box has a width of delta X, and we have another point at point B at point Y plus delta Y. Now at point O, we can have a velocity, a horizontal velocity, Vx, and that's at point X and Y. We also can have a vertical component of the velocity, Vy, at point X and Y. Now let's consider the angular velocity of the side of the square or the rectangle between O and A. So the angular velocity, or the rate of rotation, and the rate of rotation is measured in radians per unit time here, of line OA. So there's a line between point O and A, and so let's write down an equation describing the angular velocity of that small line segment. Again, it has a length of delta x. And it turns out that the angular velocity is equal to Vy at point A. So this is Vy at x plus delta x y. So that's Vy at x plus delta x y minus Vy at point x y divided by the length of the line, which is delta x. And that's the angular velocity of the line segment OA, and as delta x goes to 0, that angular velocity is the partial derivative of Vy with respect to x. Right? The limit of this quotient as delta x goes to 0 is the partial derivative of y with respect to x. Now let's look at the angular velocity of the left side of our rectangle. So that's the line segment OB. And that's equal to Vx at x, y plus delta y, shown by this arrow. So for this arm to be rotating, the x velocity at B has to be different from the x velocity at point O. And so that's measured by Vx at x, y plus delta y minus Vx at point x and y, and it's divided by the length of the line segment connecting O and B. Okay, and so this gives dv the partial as so the limit as delta y goes to 0 gives the partial derivative of Vx with respect to y. Okay, so that's the magnitude of the rotation. So now let's talk about the direction of the angular velocity vector. So line segment OA, in the way I've drawn it here, would be rotating counterclockwise. Again, if Vy is greater at point A than it is at point 0. So if the vertical velocity is faster on this side, this arm would be rotating counterclockwise. And a counterclockwise rotation, when using the right hand rule, again you put your fingers in the counterclockwise direction with your right hand and point your thumb, and your thumb would be pointing out of the board. And in this case, it would be pointing in the z hat direction, or sorry, in the k hat direction. And so this k hat direction is noted by a circle with a point. So you can imagine an arrow and you're looking at the tip of the arrow coming right out of you, out of the computer screen. So the direction of the angular velocity is again defined by the right hand rule. And in this case, for segment OA, it's coming out of the computer screen. The direction of the angular velocity of OB, if Vx is moving faster at point B than it is at point O, then the rotation is is clockwise. And again, using your right hand, you take your right hand, point your fingers in the direction of the rotation, the clockwise rotation, and your thumb would be pointing directly into the computer, into the plane of the computer. So in that sense, I guess the angular velocity of OB would be, I guess if I could show the direction, I would depict that as a cross with a circle on it. And this, you can remember this as reflecting the quiver or the feathers of an arrow that's pointing down into the computer screen. And it's directed in the minus k hat direction. And so the clockwise rotation of OB is described by minus k hat. And, I'm just realizing maybe I should have drawn the horizontal velocity arrows slightly different color so you can see what I'm talking. So that the yellow arrows are associated with the rotation of B, and the red arrows here are associated with the rotation of line OA. And so we've looked at the rotation of two sides of our rectangle. It turns out the rotation rate of the whole rectangle itself is equal to the average of the rotation rate of OA and the rotation rate of OB. So omega, again, is what we'll use to describe the angular rotation. Or sorry, the angular velocity. And that is equal to 1/2 the partial of Vy with respect to x plus the angular velocity of the other side, OB, which was in the minus k hat direction, and the magnitude was the partial derivative of Vx with respect to y, and that's in the k hat direction. And with this being the curl of V, you can see that this is equal to 1/2 the curl of V. So the curl of V is equal to twice the angular velocity. And in fluid dynamics, this is also referred to as vorticity. This is the vorticity vector. And it again gives the direction and magnitude of twice the angular velocity. So let's look at one last example. And this is an example of shear flow. It's also 2D flow, but the velocity is described by as having only a horizontal component. Vx is the only component, so we have no j hat component and no k hat component. And the horizontal velocity, again, this is Vx. And Vx is changing in proportion to y. C is the constant of proportionality. So let's sketch this. And actually, I'm gonna paste our picture here, because this regime right here is an example of shear flow. This top part up here where the horizontal velocity is constant is not part of shear flow, but this part is. So let's sketch this shear flow. So in our Cartesian plane x and y, let's just look at one point, arbitrary point, and the velocity is 0 where y is equal to 0. But as you increase in y, the horizontal component of the flow becomes faster, greater, in proportion to y. So the slope of increase in y the slope of increase in Vx as a function of y is c, our constant right here. This is Vx, which is only a function of y. So this is a picture of shear flow. So an example of shear flow might be flow of air over an airplane wing. The flow of water in a boundary layer at the bottom of the ocean, for example, or a lake or a river. Or in fact, shear flow is widely used to describe the flow of mantle beneath a moving tectonic plate. So there's a wide uses. Well, this is a simple, very simple type of flow used to approximate many situations. So you can imagine a particle that's moving with the flow, and as it's moving with time, but in addition to it moving, it's also rotating, right? And this is also shown by these arrows here in the image that I found on Google. So if we compute the vorticity at any given point in our shear flow, again, I want to write down my basic equation describing vorticity that's not too hard to remember. The component of this matrix, and here Vx is the only non-zero component. And this gives minus k hat dvx dy. And so as I've drawn this rotation, you can see that on the top part of a particle will be moving to the right faster than the bottom part. So the sense of rotation will be counterclockwise. And so the angular velocity vector or the vorticity vector will be, again, put your right hand with your fingers in the direction of the clockwise rotation and your thumb points downward into the board, and so and that's in the negative k hat direction. And so in this case it will be minus k c. So the vorticity in the simple shear flow is constant, okay, everywhere, and it's pointing downward, representing a constant rate of rotation everywhere here. And even though as you move further in y, the particles will be translating faster, they'll be rotating at exactly the same rate as a particle here that's not translating in r, but just rotating. The vorticity field is constant here. And that's also depicted by these constant sort of circles shown in this diagram. So I think that about concludes this discussion of curl. You'll be able to compute the curl based on this equation, given a function of x, vx, vy, vz of this vector field, and given a pattern of a velocity field, knowing, for example, how things might be rotating, you'll be able to relate the curl vector to that velocity field.